Welcome back, everyone, to part 2 of our lab intro for the week of October 19. We will be doing exercise 10 from Contemporary Activities in Astronomy by Hoff and Wilkerson. So what we're doing here is we're measuring something known as trigonometric parallax. And trigonometric parallax was predicted. Astronomers knew that trigonometric parallax must exist among the stars once we realized that the Keplerian Copernican model of the solar system was probably the better model of the solar system, and that the Earth was moving through space. If the Earth is moving through space and moving from one side of the sun to the other side of the sun, you should be able to see foreground stars jump back and forth relative to background stars. So let's actually draw this up here first. Is to say there's the sun and there's the Earth, and the Earth moves from one side to the other side. And if you got a foreground star and a background star, the foreground star seems to, if that background star is very far away and not moving, the foreground star seems to move quite a bit from one side to the other side. Since this is one astronomical unit, we can say we have a simplified version to measure the distance to this star. If you have an infinitely far background star, the distance to this star, the distance d, is equal to 1 over p, where p is that angle in there. And so that's the parallax angle. This, just like we had a special form of Kepler's third law, p squared equals a cubed, it's only true for objects in orbit around the sun. And you had to measure p in years, and you had to measure a in astronomical units. This only works if your distance is in parsecs. 1 parsec is 3.26 light years, and your angle that you measure right there, your parallax angle, is in arc seconds. So if you get your distance in parsecs, and you have to be observing from the Earth. And have the Earth, if you're observing from Mars, you're going to get a bigger parallax angle because you're moving out here further. If you're observing from Venus, you don't have as big a parallax angle. So this is great. This is the way we measure distances to stars. It took a very long time to measure the distance to the first star. Generation after generation of astronomer came and went, lived and died trying to make those measurements. And this is the book that I started to show you a second ago. This book by Alan Hirschfeld, Parallax, The Race to Measure the Cosmos, is a fantastic scientific detective story. Well worth the read to the story of trying to make this measurement of parallax. And so the first parallax measurement wasn't made until 1838, I think it was, in here by Bessel, who finally measured this. And remember that the Copernican model of the solar system was proposed, the Keplerian model of the solar system was proposed and more or less supported by Galileo as early as 1610, 1620, and then we had all of the work of Newton that we talked about through the 1640s into the 1670s. And remember the measurements of Uranus and Neptune and all of that work and so on. And so we did a lot of work measuring in the solar system. And when we did that, we have this, we still couldn't measure parallax. And the reason is the nearby stars are even so far away. This distance is so far, that parallax angle is tiny. The nearest star is more than 1 parsec away. So it's the angle of shift that you see is less than 1 arc second. And it's hard to measure things accurately to less than 1 arc second. The optics just was in the way, atmospheric turbulence, other things, other effects going on that made this a really challenging measurement to make. And then to actually know that you made it, to know that it just didn't look like it had shifted a certain amount. And so we're gonna practice these measurements, measuring things, the distance to objects via trigonometric parallax. Just as we had to do in the lab where we measured the mass of the moon last week, we need to use a different version, a more generalized version than what you see right there, and because that's where we won't be the Earth in orbit around the sun making these measurements. We're going to go outside. You're going to use your angle measuring sticks that you made. You got to bring your angle measuring devices, and we're going to go outside, and we're going to have a person stand here, and that'll be our foreground star. And we'll line that person up with some distant object that's out there a long ways, a light pole, a tree, or something along those lines. And then we will walk back and forth here. This is called the baseline. We'll have that distance d that we can measure directly with a tape measure, one of those big long rolling tapes like we used first week in lab. And we will measure this person's angle along that line that way. And on the top of page 98 in your book, right there on the top of page 98, you can see a table that helps you figure out what you're going to get here. You've got this interior angle that's theta equals 2p, it shows you. And what you're actually measuring is B and A. So you're measuring that angle. This is, if that star is infinitely far away, that's a straight line. Otherwise, it's got that something like that. And you can see this idea. It walks you through in the lab how to get turn B and A into theta, into the 2p that you want to see right there. And you can see this. If we could walk through this a little bit here right now, right? Suppose that angle is P, and that's 90 minus B. That's going to be right there, and that's 90 minus A, and that's P right there. And so you can start to see if that's 90, and that's 90, then all of these things have to add up to 180, 180, and 180 around this direction. So 90 minus A plus 90 plus P have to be equal to 180 degrees. But that means P has to be equal to A, right? Because you got your 180 degrees right there, and those things have to cancel out. Likewise, over here, P has to be equal to B. So if you measure A and B, 2P has to be equal to A plus B. We can walk through that a little bit more in class on Tuesday or Thursday, whenever you're in class this week. We'll talk about that just a little bit more. But the idea here is to say, you know, there are a lot of things that could make this measurement go a little bit weird. Like, for instance, if the baseline isn't perfectly perpendicular to this line right here, you might have one of these angles bigger and one of these angles smaller. That's why you want to do this both ways, and to get measure A and B, and to say that P is A plus B over 2, and do this. So go out there and make those measurements. Where B is the angle between your distance, you're holding up your angle measuring device and measuring the angle between the foreground star, your lab partner, and the background object. It could be another lab partner. There's 4 of you. So what I'd like for you to do is I'd like for you to make this measurement twice at 2 different distances. So you have different people with different angle measuring devices making this measurement. So do this where this distance is the distance that you have to the person is, let's say, 10 meters, and then have the distance of the person be 20 meters. So you go outside and make this measurement at 10 and 20 meters and see if you can see what the difference is in terms of, and you can adjust your baseline accordingly. That's your S value, right? And so you've got your S value right here is, if you take this whole thing, let's just do half a triangle to start with right here. And let's just call that S and call that P. And then if this is R, and so we know S over R is equal to theta, or 57.3 S over R, we've been using that a lot, is equal to theta if you're measuring in degrees. And so you measure your S baseline, and what you're solving for here is R is the distance. So you want to find the distance of the distance that you measure via parallax. So that's distance via parallax. And then you want to measure the distance directly with your tape measure and compare those two. This is kind of like what we did in the lab when you measured the person's height a couple of weeks ago to do that comparison. So what I'd like for you to do is to measure R via parallax divided by R via direct measure tape, using the tape. Okay, and if your parallax measurement is right on and this measurement's good, that should be equal to 1. My guess is it's not going to always be equal to 1. So what I'd like for you to do is to make this measurement twice. So you'll have this at 10 meters twice and at 20 meters twice. That's R. So I want R to be equal to 10 meters and this to be equal to 20 meters. You choose your S. You choose your baseline to be whatever you want your baseline to be, such that you get a reasonable angle measurement, right? You don't want too big an angle on your stick, but you don't want such a small angle that you can't see. So maybe that's 1 meter, maybe that's 2 meters, maybe that's 5 meters. You select S. You're the scientist here. You're doing this experiment. And so you go out, you select S such that you get a theta that you think you can get a good, comfortable measurement with your stick. And then swap people around and do it again. So you get 2 measurements at 10 meters and 2 measurements at 20 meters. And then come back in and write it on the board like we did with the angular resolution stuff. I'd like to know what this ratio is on the board. You don't even have to do that ratio if you don't want to do that ratio, because we know it's 10 meters and 20 meters. Okay? And so I'd like to see just, I think it's fine for you to come in and write on the board the R measured via parallax for 10 meters and R parallax for 20 meters. Okay? And then we'll see, the whole class writes up there, and we'll break it and we'll talk about what we see. Do we see a trend in that? Do we see something that's telling us something interesting about our ability to measure the distance via parallax? So what I'd like for you to do is to, when you've done all of this, I want you to turn in and show me your work again, like you did for the other part of the lab. So show me how you did it. Walk me through how you set this up and how you made your distance measurement via parallax, and walk me through all of your calculations and show me your data tables. And then I also would like you to write a small paragraph about what we're seeing. What do you see here? So write me a summary of what you see right there. And then you should also be able to, there's some questions in the end of the lab that's about the astronomical parallax, the D equals 1 over P kind of thing that only works for Earth in orbit around the sun. And so I want you to do that analysis of what you see in that table and talk to me about the causes of any issues that you see in there and what you think is going on. So you can do that instead of answering discussion questions 1 and 2 in the back, but I would like you to answer questions 3, 4, and 5. So answer 3, 4, and 5 out of the back of the book, and that reminds me, let's go back and think about exercise 6 again. You're telling me, you're reporting to me what you see in terms of the resolution of a human being and what you see in terms of resolution of the telescope and how much of an improvement or not an improvement it is or whatever. But then you should be able to answer all 3 questions for exercise 6. So answer all 3 questions for exercise 6, 3, 4, and 5 for exercise 10, and then write me a little bit of paragraph about each one, summarizing your observations and what you see. And that's what you got. So let's get you going. You should be able to get set up and to do this. Practice to make sure that you see what these angles are and that you can look at the diagram at the top of page 98 and see if that diagram makes sense to you. And then you can be ready to go in lab when you get there this week. And we can start working right away and work right through this. So that's what I got for you. That's your introduction to the lab this week. And I hope that all's going well. And we'll talk more about this when you're in lab as you have questions. But you should be able to come to lab and be ready to jump right in and do this work. Take care, everybody. Enjoy the rest of your weekend.